Okay, so let's get started. Good morning, everyone. I wanted to back up a little bit and start here in our last slide of the first presentation on differential equations, because at the end of last class, when we finished this, Michael Adam mentioned the interesting study that's going on with the wastewater in Boston to track the amount of virus that's in the city and its vicinity, and how incredibly accurate the rise and fall of the bacteria virus in the wastewater was to predict as a leading indicator of just what kind of hospitalizations and even death rates were found in that area. It was really quite a remarkable thing that can be so accurate. The amount of bacteria, Omicron bacteria or COVID bacteria in the wastewater. And Mike suggested that there was a website to go out to take a look at that. And this is one of the graphs from that website, which shows the amount of COVID bacteria in the wastewater. And that tremendous spike there is January of this year, in the winter, that tremendous spike of the original Omicron. And it is quite incredible that the growth is absolutely astronomically exponential. And then what's so interesting, it falls as quickly as it was rising. We all know that nothing grows up to the sky. You can't have infinite growth. You'll just run out of material. But what is it that is stopping at some point the incredible growth and actually bringing the amount of bacteria or virus down almost as quickly as it comes up? What you're looking at here is the differential equation from the last slide. This is the exponential growth, where the rate of change of the amount of virus is proportional to the actual amount of virus, which is measured in the variable z. Z is some computation, some functional value of the time. It's going to be an exponential function of the time. What would cause that spike to come down like that? Well, it turns out, and Mike gave me the reference to this, that there's a modification of this very differential equation, which will bring that curve down as dramatically. And let me read to you what Michael Adams said in his email to me to explain this. He said, the infection spreads and samples rise exponentially until the entire population susceptible to the infection gets it, and then starts shedding the virus, although many of those infected don't have symptoms. That's what happened in mid-January. That's what we're looking at, that incredible spike. Then the infected people get better. Okay, this is the good thing about the Omicron, that people don't get all that sick. And most people do get better pretty quickly, just after kind of a bad cold, in about a week, and they stop, therefore, shedding the virus. With no new hosts available, that is, everyone who's going to get it gets it, and there's no one else so susceptible, the virus begins to shrink very, very quickly. And so that's the real world explanation of that. And this phenomenon was actually studied back in the 1840s by a mathematician by the name of Verhulst, and he created this first version of this differential equation. And there it is. There's the modification. Here's the new differential equation, which explains this incredible spike down. And you can see the original growth, and then a negative sign, and this additional term. And this additional term, again, we find z in it, the computational rule of the function itself. Now it's squared. So we're bringing it down very, very strongly as if z is big, divided by this constant k. And this, again, is another one of these real world constants. It's called the carrying capacity. And that's what Mike is referring to as the susceptibility. How many people in the population, or percentage of the people in the population, actually are susceptible to this particular virus. It's not 100%. And since it's not 100%, at some point, this thing will collapse, and will collapse according to that differential equation. Obviously, the details are something that we're not going to go into. I just wanted to show you the idea of another differential equation, a modification of the original one, which will lead to that kind of growth going down. And this is the solution to that more complicated differential equation, a more complicated solution. You can see that k is there and it's still exponential with now a negative instead of a positive growth. And the constant c is dependent upon the initial population that you start with. So here's a new differential equation, a new solution, now modeling this kind of behavior. And these are the different graphs that will show different kinds of solutions to this equation, depending upon what A is, the actual growth rate here, A, different models. So this is what epidemiologists do. This is what population, and data scientists do, is work with differential equations like this to model what is going on and make predictions, understand what's going on and make predictions for the future. Mike, is there anything you want to add to what I've said in terms of this, my explanation?
Just that I was looking at this chart fairly regularly in December and January, and it's scary.
Yes.
I mean, you look and it goes way back to the beginning of 2020. And in December and then January, we were seeing it, 10 times higher than it had been in all the other outbreaks.
Yes.
So I started wearing my mask more religiously about that time.
Yes, that also could be, that's one of the things I suggested in my email, that maybe this kind of thing, everyone getting around you getting sick, maybe you start changing your behavior a bit, which also can help bring down the amount of infection. What this points out mathematically, if you allow me to just go back to be the math teacher for a second, what this shows is that these equations have a domain. Remember the idea of what are the values that you can put into your computational rule. And there are sometimes natural restrictions. There are mathematical restrictions. You don't want to ever put a number in so that it gets zero in the denominator. But also there are natural numbers that you just don't want to put in because they don't make sense. And in this kind of equation here, you just can't make time be bigger and bigger and bigger and bigger. Because as you make time for the growth rate, for example, the simple one, well, it'll just go to the sky. And there'll be more people, the math will predict more people infected than there are people in the entire planet, because the time is just totally unended. So there are these natural boundaries of where the domain of these rules, of these mathematical models, makes sense. The model will break down after certain values in the domain. It's not a mathematical restriction, it's something from the real world. And what that is here would be the so-called carrying capacity of your population. At some point, that's going to limit how much time this kind of crazy growth can go on before it finally stops. Okay. All right. Well, again, thank you, Mike, for sharing that with us. I thought that was a nice example of yet another differential equation. And the nice thing about it is it was an adaptation of the one that we were originally looking at. Okay, I think we were here when we left off. We were just about to start the second, I'm sorry, this is where we get through this. This was the first, the divisibility of the Achilles and the tortoise. I'm sorry, running through this. All the pieces, yeah, we were here. Looking at the second paradox that we wanted to look at from Zeno, and this is called the paradox of the arrow. And it's stated up there in red in the box. At any point in time, the arrow can only occupy one particular position. If you freeze, stop frame, the photograph, it's at any one instant, it is one place. And so therefore, how is it moving if it's always in one place at any particular instant? And this is, again, Zeno's philosophical argument that some sense, motion is impossible, or at least very, very problematic. I wanted to use this to make an illustration of the business about that. How does that average rate of change turn into the instantaneous rate of change? So here we have an arrow, and it's going to move in time in tenths of a second. Starts at 0, and after a tenth of a second, the arrow is there. After 2/10 of a second, the arrow is there as it moves towards the target. Okay? And it'll pick up a position. At the beginning, it'll be at 0, then it'll be at 1, be at 2, whatever the units are, meters, feet, miles, makes no difference. Okay? And we can ask the naive question, how fast is the arrow going? Well, we know we can ask that question in terms of averages. We can ask, well, what is the speed from 0 to 0.1? That's a legitimate question. That's a simple question to ask conceptually. It's the change in position over the change in time. The change in position seems to be 1, and the change in time is a tenth, and 1 over a tenth is 10. So it's moving at 10 meters per second in that time from 0 to 0.1. And since this is a constant motion, no matter where you take that average, you're going to get the same number. From 0 to 0.2, well, that's going to be 2 divided by 0.2, which is also 10. You can go into intermediate. You can go from 0.1 to 0.2 inside. And again, it's going to be the same calculation. The average will not change because the arrow here that I've depicted is moving at a constant speed. So it's not such a stretch, no matter what interval you pick, we're always getting the same speed, 10 meters per second. It's not such a stretch then to ask Zeno's question, well, what is the speed at 0.1 or at 0.2 or at 0.1.5 or whatever time you want to pick? We're more comfortable in answering the question 10 because it seems to be always 10. No matter how you pick that average, you're always getting the same number. So asking what's the speed at that instant, well, it's the same. It's always 10, no matter what. So this is kind of an easy answer. What gets tricky, where Zeno's question becomes thoughtful, at very least, is when we go into something like free fall and we drop something and it's moving faster and faster all the time. And then Zeno asks, okay, how fast is it going after the first second, at that instant? How fast is it going then? That's not so easy to answer. That's where we need to introduce the business of the derivative. That's where we have to introduce the idea of taking those average speeds and shrinking down the time interval smaller and smaller and smaller to see if we can find a pattern of where that speed seems to be locating around, as Strogas calls the best average that we can use for that instant. That's the idea of the derivative. And these ideas, as you can see, go way, way back, all the way back to the ancient Greeks, answering these kinds of questions, looking at the potential paradox of asking for a rate of change when there is no change. And that's what Zeno is after here. And that's why I wanted to bring it up. It goes back in our intellectual history. And speaking of intellectual history, one of the great giants of that history, of course, is Plato, considered the greatest philosopher of the ancient world and one of the greatest philosophers of all time. And his influence on our view of mathematics is profound, besides his influence on many other things. And it comes from this idea, this general idea that we live in two kinds of worlds. We live in the real world, senses, but that is actually not the true reality. The true reality of the universe, of the world, is our mental world, the world that we see in our mind's eye. And the best example of that real world, the real world of ideas, of ideals, as he called it, is the world of mathematics. He was, obsessed with the idea of mathematics and how it should be done, and because it was the ultimate example of this world that he felt was more real than the world that we live in, the world of the senses. And a good example that he would use is, for example, the circle. What is the circle? Well, the circle is a locus. It's the set of all points equidistant from some central point. There is no circle in the real world. There is no thing, there is no physical object that you can point to or draw in which every single point is exactly equidistant from that same central point. Every engineer will tell you that. There's no way to make such a measurement. Every measurement has an uncertainty of a certain amount. We're not even getting into Heisenberg's uncertainty principle yet. We're just talking about the way that we can measure things. We cannot measure things exactly. There is no way for us to do that. You can't go out past, generally in measurements, you generally can't go out past 8 or 9 decimal points. Okay, but the locus of a circle, it wants to go out to an infinite number of decimal points. Okay, because the locus says it is the set of points that are exactly equidistant from some central point. There is no such circle in the real world. It only exists in our minds. But what's the amazing thing is that Euclid has 13 books of theorems filled with these true statements of these kinds of objects that don't exist except in our mind. This is the point that Plato was trying to make. And because of this world of mathematics, there are certain restrictions that he feels are legitimate to put on how mathematics is done. And this was by and large followed very much so, for a long, long time. And when people tried to move away from these restrictions, well, that was done, quite with the knowledge that this was somehow or other beyond, beyond the normal methodology of mathematics. Someone has asked that I do the enabling, so I will do that. Okay, we've got the voice on. So I introduce Plato because and this view of mathematics, because it is one fact that dominates mathematics still to this day in many ways. This view that comes to the basic question, is math invented or is it discovered? And the Platonic view is that it is discovered, that mathematics is out there already, that these ideas, these mathematical objects, and therefore the theorems that we prove about them exist in this world of ideals and forms of Plato. And what mathematicians are doing are just discovering what's already there. That is still a very, very prominent view among mathematicians. The other basic view is that we invent these ideas. We develop these definitions, we decide what axioms we want to use, and then we proceed using logic and mathematical pictures to discover our theorems. And the joke is that mathematicians are Platonists on Mondays, Wednesdays, and Fridays, and they're constructivists on Tuesdays, Wednesdays, and Saturdays, and on Sundays they don't know what they don't know what they think. But all mathematicians will tell you, all research mathematicians, not me, I am not a research math, but all research mathematicians will tell you that there is this overwhelming feeling when they're working on trying to push these new ideas, that this stuff is out there. They're trying to see what it is, this overwhelming feeling that this has an independence beyond themselves. It's just an amazing thing about the world of mathematics.
And where do you fall in that spectrum, Peter?
That's a good question. I guess I am in a sense of that Monday, Wednesday, and Friday. I really am of the two minds. So it's really probably the best answer that most mathematicians will give. There are some ideologues who definitely have the one position, but I would imagine most mathematicians would say, yeah, the Monday, Wednesday, Friday solution is probably the best, because there are these two very legitimate feelings that we have about mathematics. On the one hand, I feel I'm constructing this stuff, I'm picking my axioms, I'm looking through the pictures to try to see what consequences I can derive from my ideas, and the other one is that Platonic idea. So the statement that I want to leave you with Plato is down the bottom, and you do not know also that they make use of visible forms and reasons about them. They are not thinking of these, but they are thinking of the ideas, the ideals which they resemble. They are really seeking to behold the things themselves, which can only be seen with the eye of the mind. And this is where this mind's eye comes from. The phrase, the seeing it in your mind's eye, comes from the writings of Plato. He's the first one who kind of used that kind of metaphor. Okay, given that kind of restrictions from Plato, I want to now introduce the three great problems of classical geometry. Question was asked very, very early on in our course: where did these theorems come from? Where did the problems come from that fills up Euclid's 13 books? Was it just starting with these axioms, just blindly proving one theorem of another? No, that's not the way mathematics develops. Yes, when you look at Euclid's books, that's what it looks like when it's the finished product, but that's not where it comes from. Most mathematics comes from solving problems. And these are the three great problems of classical Greece, which led to so much new mathematics, which led to so much of what filled in Euclid's books and beyond, and Archimedes' books and whatever. We're going to take a look at these three problems and look at one very important new discovery in mathematics, a new invention, if you like, in mathematics, coming from studying each of these particular problems. So the first problem is called the squaring of the circle. The idea is to take a circle, take a simple circle of radius 1, and to produce a square that has the same area. Remember, in geometry, in Greek geometry, we want to construct these things. We need to construct the square. We need to construct the proper side, and then the four sides, that the area of the square is the same area as the area of the circle. Now, of course, for a radius 1, the area of the circle is going to be pi. It's pi r squared, but r is 1, so 1 squared is 1. So we're looking for a square who has an area of pi. That means we need a side of the square root of pi. The square root of pi times the square root of pi is pi. We need to construct a length of the square root of pi. Yeah, this is not going to be easy. This is, in fact, going to be impossible in the restrictions that Plato is about to lay down. The second problem is called the duplication of the cube. We have a cube that's 1 on a side, and the volume of a cube is 1 times 1 times 1. It's the length times the width times the height. So we have a volume of 1. The challenge is, the problem was, create a cube that has a volume of 2. Now, if you want to create a volume of 2, then you need a side of the cube root of 2, because the volume is going to be the side times the side times the side. Therefore, it will be the cube root of 2 times the cube root of 2 times the cube root of 2 would in fact get us 2. So to construct this box, we need to construct a side, a length of the cube root of 2. This also is not going to be easy. Okay, this is going to lead to great investigations and trying to find different kinds of ways of doing this. It's not doable according to the restrictions of Plato. People have to work beyond the box that Plato wants to put us in. Mathematicians refuse to be put into such boxes. And the last problem, the last great problem, is the trisection of an angle. To take any arbitrary angle and divide it evenly into 3 parts. Sounds easy. Sounds certainly easier than the other 2, but given the general angle, this also is something that cannot be done. Cannot be done in what way? Cannot be done the way Plato says it must be done. He lays down the rules that you can only use an unmarked edge, not a ruler with marks, with hash marks, measured marks, just an unmarked straight edge and a compass. With those 2 construction tools, can you construct a side of length, the square root of pi? Can you construct a side of a length of the cube root of 2? And can you construct this 1/3 of this angle? Can you find a way to draw that line there, which is 1/3 trisects the angle? Can you do it using these tools? Why does he insist upon using these kinds of tools? Because if you didn't use these tools, if you used other mechanical means, he said, you would set aside and destroy the whole of geometry, since it would reduce these things to the senses, and that would corrupt the internal images of thought. Using these tools are okay. They seem to be compatible with the world of ideals. Anything else brings in some kind of a real world, sensual corruption of the beautiful world of mathematics and is illegal as far as Plato is concerned. You say, why listen to Plato? Well, I don't know. This is why the astronomers right up through Copernicus, including Copernicus, only dealt with circular orbits for the planets. Why? Because Plato said so. Plato said that the planets are like gods in the sky. They are also an example of this world of ideals, of forms, and the perfect form for the motion of the circular planets going around the Earth can only be circles and combinations of circles. And those are the kind of mathematical models that you can build. And people followed that until Kepler. They followed that until the 1600s. They followed it for 1800 years because they believed Plato made the argument that this is the only perfect form to use for the motion of the planets in the sky. This is the kind of influence that Plato had. So let's go through these three examples, these three problems, see how they were tackled and see how they each led to at least one great advance into the area of mathematics, looking at different ways of doing mathematics, bringing in new ideas into mathematics by going beyond Plato's rules. The mathematicians were not going to be hampered in by his rules. Trisection of an angle. Turns out it's very easy to trisect a straight line. Here we have this line AB. We want to divide it into three parts. Euclid shows us how to do this in his books. He says, draw any convenient line at an angle, any line that you like, and mark off from your compass a nice simple distance C. Now, open your compass to a certain distance and hit the compass, from A to that edge point. And do it again. Keep the compass open to the same amount. Knock off another piece and keep that compass at the same size and knock off one more distance of C. So now C, D, and E, they certainly are, three equal pieces. I constructed it this way using my compass. Euclid says, now simply draw the line EB. Okay, we can do that. We have this point E. We've constructed E. It's 3 times further out than AC by the construction. And now we can draw the line EP. Euclid says, now simply draw the two parallel lines from C and D. Drop parallels of EC from C and D. Mark those points F and G. And we've now just trisected the line. We've trisected AB into F and G. Why? Because this little triangle here, ACF, is similar to the big triangle AEB. And since AC is 1/3 of AE by construction, therefore by geometry, this must be 1/3 of this in corresponding parts. So it's easy to trisect a line segment, but yet this is not something that can be done with ruler and compass, to trisect an angle. Very, very interesting. It cannot be done. By the way, the fact that these things cannot be done were not proved until the 19th century, so the 1800s. Finally, when mathematicians finally were able to prove that these things were not possible using the tools of Plato, of a straight edge and a compass. It took that long. So people continue to try to push the envelope using different kinds of methods because the straight edge and compass was not working until finally in the 19th century. So stop trying. It is not going to work. Here is a proof that these tools are inadequate to do these three jobs. So here is the first new idea, a very important idea for us for the calculus. All three of these will be important ideas for the calculus. That's why I'm bringing them up. I'm not giving you a presentation on the history of geometry or Greek geometry. That is not what I'm doing. We're staying with the history of calculus. And this new idea to trisect the angle is right in our wheelhouse. This is the first time we see that a curve is constructed from motion. Okay? And it's a very, very beautiful and elegant construction. We have this line here, HG, it's going to fall down at an even rate. And we have this radius line here, it's going to fall down at the same rate. This radius line will fall down, the straight line will fall down, and where it intersects as they fall down, will create this curve. It has two names. It's called the trisectrix because in here it's going to help trisect an angle. Notice this is we're way away from Plato's straight line and compass here. We've got two motions, two simultaneous motions creating a locus. This is the first time this is done in the history of mathematics. And it's also called the quadratrix because also this can be used to solve one of the other problems of squaring the circle. That we're not going to look at. We'll just look at this application here. But it's defined using motion for the first time. Remember, most of Greek geometry is very static. So here we're going to try to trisect this angle here, okay? And I picked here this angle of 75 degrees. This is a picture from my mathematical. We'll be looking at that in a moment. Okay? So we want to trisect 75 degrees. Well, as I just showed, we can certainly trisect 0 to h. We can trisect this height here. Okay? This here, OA is 1/3 of OH. That we know how to do. Euclid shows us how to do that. Well, all we need to do is just draw the parallel line across, okay, from A and see where it hits the trisectrix. And this angle here must be 1/3 of this angle here. Why? Well, if this is 1/3 of this, and they're both falling down together at the same rate, and this OA is 1/3 of OH, then this angle here must be 1/3 of this angle here. And this is the trisection of that angle of 75 degrees. And of course, any other angle will do using the same trick. Okay? A very, very elegant solution, very far away from the rules of Plato. Plato would not consider this a legitimate explanation. Okay? But it is very beautiful and very groundbreaking mathematics. Let me show you the moving picture of this. It's very pretty. The trisectrix. Let's look at the animation first. This is what I mean. The curve is being created by the motion of these 2 points. The simultaneous motion of this line dropping down and this radius line also dropping down. These 2 points will hit the bottom at the same time. They're moving down at the same rate. Here I am simply just keeping track of my 1/3. I'm keeping track of my division by 1/3 of the particular height. Okay. So let's take a simple point here.
Peter?
Yes.
But Hippias is doing this work prior to Plato, according to the dates, right?
Yes, this is done prior to Plato. Yep. Actually, he is a contemporary of Plato, more or less. Yeah. I'm sorry, I think Plato was born just around this time of 425. So this is very early work. Very early work. Yep. Yeah, mathematicians were working with all kinds of things before Plato got around to setting rules. Mathematicians are not ones to follow rules, except their own internal consistency rules. So here is, for example, I wanted to take a simple, here's a simple example. I'm down halfway from 1. So here my line is 1 and my angle here is 45. Okay? And all I need to do then is to do that little construction. Okay? And just take that 1/3 distance here, draw my line, and I'll wind up with an angle of 15. So the angle of 45 is trisected by 15 by that same construction. And I can just simply keep track of that as I go, always knowing where the angle trisection is. What's important for us is not particularly finding the trisection of an angle, as interesting as that would be for geometrists, given this problem that they pose for themselves. What's interesting for us is that this is the first curve that is defined not by a static locus, but by a locus of moving parts, moving pieces of motion itself. Okay, first with innovation. Yes.
It also means that we can divide the angle into any number of parts doing the same thing.
Very good observation. Not only does Euclid show us how to divide something into 3 parts. He shows us how to divide it into n parts. And yeah, so you can divide up using the trisectrix, you can divide up an angle into as many parts as you like. Very good observation. Thank you.
Even approaching infinity, just saying.
just saying. Fair enough. Okay, second problem, the squaring of the circle. This is a little bit tougher, right? Now we're trying to construct radical pi. I mean, never mind pi. We're trying to construct the square root of pi because, right, the area of the square is the side times the side. So we need the square of the number to give us the area of pi. So we don't even want to construct pi, which is hard enough, given the fact that it's an irrational number. We want to construct the square root of pi. This is a tough one. Okay. Let me show you again a simple one that the Greeks were able to do. Take an arbitrary rectangle, and we can, in fact, construct a square which has the same area as a rectangle. I want to show this I have a method to my madness of why we want to look at this. And it's a nice construction in itself. We take the length and the width, A and B. We move the width up here to B. So we have a long, long line where we combine the length and the width into this big line AC. And then we draw a circle using that AC as a diameter. And from the point B, where we move this thing up, where the length ends, we construct a line straight up to the circle and call that S. It turns out that you can prove that S squared is AB, but AB is the area of the rectangle. So S is, in fact, the distance that we want to know. We can prove this by showing proportional triangles. We can show that this triangle is proportional to this, and therefore A is to S as S is to B, and you cross multiply and you get this equation. S squared is equal to AB. The important thing is that S squared is the square on S. Okay, and since AB is clearly the area of the rectangle, length times width, we have now created the quadrature of the rectangle. So finding the quadrature of a rectangle is relatively easy using this construction. By the way, there's more. I've shown the more detailed proof of this. If you're interested, the geometries in the class, if you'd like to look at this proof that S squared is equal to AB, it's at the end of the end. It's the next slide underneath end. In your presentation, I give a more detailed Euclidean type proof of this very nice result. So yeah, we can find the quadrature of a rectangle relatively straightforwardly. What about the quadrature of a circle? Well, here we have a man again before Plato, very, very early on, by the name of Hippocrates of Chios. He's not to be confused with the great doctor Hippocrates of Kos, same name coming from 2 different city-states. Hippocrates is important in the history of geometry for a couple of reasons. One is he's the first one who wrote a book of elements, very much like Euclid's. Okay, he's the first one who sat down and took at his time all the elementary geometry that was known and put it into a book. Interesting to point out at this juncture that the reason why Euclid's book is the first book of geometry that we have is not because many people think it's the first geometry book that was written. It's because it made all the other books obsolete. When Euclid wrote his elements, everything that came before it was in, anything that was important in elementary geometry was there. It made everything that came before it obsolete because it was all in there. And since copying books was expensive and time consuming, why copy books, old books that have partial results and maybe even incorrect results when you have this incredible work of Euclid? And so just the copying presses just stopped from anything in geometry, anything in elementary geometry, except for Euclid. That's why Euclid is the oldest text that survives, because people just stopped copying anything else. But apparently Hippocrates did write a version of the elements, which has not survived for that reason. He was not able to square the circle, but he went ahead and tried to take another form, kind of a piece of the circle. And this is interesting in the history of integral calculus, finding areas. This is the first time an area other than a area bounded by straight lines was found. Okay, and the area that he worked with were Loons. these half moon type figures, which are called loons. The way you draw a loon is you need two circles or two semicircles. You have a big semicircle here, and you draw a chord. And then from that chord, you use that as a diameter of another smaller semicircle. When you do that, you cut out a loon, right? Because the bigger semicircle will cut out a piece, and what's left from the smaller semicircle is called a loon. Another interesting and important thing about Hippocrates is that this proof that I'm about to show you is the oldest proof that we have in mathematics. Okay, it was finally written down in 500 AD, okay, by a Roman commentator, but he has source material that we no longer have, that doesn't exist. He still had a piece of work that showed Hippocrates' original proof, and he reproduces it in his work. And his work has come down for us. He says, as Hippocrates wrote 900 years ago, for him, this proof was 900 years old. For us, it is over 2,000 years old. This is the oldest proof that we have in the history of mathematics. Another interesting thing about the work of Hippocrates. And the proof is very nice. We'll just go through the highlights of the proof. The key to the proof is to know the fact that the area of a circle is proportional to the radius squared, or to therefore the diameter squared. And you can write down this proportion, that the area of one circle is to the area of another circle. Again, I'm using these square brackets to represent the area of. So the area of the two circles are in the same proportion as their diameters squared. This is a statement which is true. Euclid proves it in book 12 of the Elements using the method of exhaustion. Hippocrates just states it. We don't know how he proved this, or even if he had a proof. He just knew this intuitively. This will be the heart of Hippocrates' proof that this loon has a quadrature. The area of this loon is going to be the area of this triangle. That's why I've got them shaded the same way. But the idea of the proof is, we draw this triangle, this right triangle here with B in the midpoint. It's easy to show that this is a right angle. It's easy to show that this is an isosceles right triangle. And therefore, by the Pythagorean theorem, this squared plus this squared is equal to this squared. But these two are the same, okay? And so knowing that from the Pythagorean theorem, this thing squared is twice as big as this thing squared. But this is the diameter of the big circle, and this is the diameter of the small circle. So if this squared is twice as big as this, then this circle is twice as big as this, by this fundamental proportion. Now that we have this big circle twice as big as the circle creating the loon, the proof is very, very simple. Okay, we can just say it in words. Therefore, the quarter circle of the big circle is exactly equal to the half circle. If the quarter circle is exactly equal to the half circle here, then look what we have. The half circle is equal to the loon plus this sector, and the quarter circle, equal area, is equal to the triangle plus the same circle. And therefore, the loon is equal to the triangle. We know the area of a triangle. Hippocrates has found the area of the loon. This is the first time in the history of mathematics that we have an area of curved spaces. This, of course, is what the integral calculus is all about. And the rest of these lines here is just a color coding of the words I just said. Okay, that's all that is just showing those different pieces are equal and add up properly. Yes, this is not going to get us very far, right? This is very, very far away, even from Archimedes' triangles, which he fits in very carefully. We're very far away from the dumb idea of the rectangles. But yet, this is a great milestone in the history of mathematics in many, many ways. Mathematicians are determined to try to find areas of all kinds of things. He takes a very stylized figure. Yes, this is not an arbitrary, crazy, wiggly figure. It's a very stylized figure, but yet he is able to accomplish this. Okay, we see the growth of mathematics as we see these things. So that's the second idea here. When people Hippocrates himself continued to try to work on this problem, try to expand from the loons to the circle itself. Not successful. The loon idea didn't lead anywhere. We have a new idea coming from someone else, Antiphon, who again is someone who lives around the time of Plato, a little bit before. He has this idea that I think would occur to anybody after a while, that, okay, we're looking for the area of a circle. We're looking for the circumference of a circle. How do we try to calculate this? Well, if we inscribe these regular polygons with more and more sides inside the fixed circle, isn't the perimeter of the polygon getting closer and closer to the circumference of the circle? And isn't the area of the polygon getting closer and closer to the area of the circle? Isn't this a way to try to attack the problem of finding the area of a circle? Okay? To try to find that ratio pi. And this, in fact, will work as an idea, and let me show you. This will work. Here we have the number of sides. We'll start with a triangle. Let me go to 6 sides before we catch our breath. Okay, here's the hexagon version of this thing. And I have 4 numbers to show you. The number in blue is the height of these rectangles that I'm creating. Okay, it's 0.866. The radius here is 1. I've got a circle of radius 1. Okay, so I'm showing you the height of the triangles that I'm making. I'm showing you the value here, 1, which is the length of the sides of the triangles I'm making. This is the one number which is easy to know. When we have an octagon, this is a 60-degree angle, and therefore this is an equilateral triangle. If these two are 1, this is also 1. Okay, so in fact, the sides here are 1. Therefore, the perimeter, which is the 3rd number in red, this is the sum of all the distances around, and that would be 6. There are 6 sides. And finally, this number here is the area of the circle. It's 6 times the area of any one of these triangles. And so these are the 4 numbers that I'm keeping track as I'm making my sides higher and higher. And as you see, as we make the sides higher and higher, we get to 12 sides, for example. Here now the side now has shrunk. I'm sorry, the height has gone all the way out to 0.966. It's getting closer and closer to 1, but always less than 1. Our sides are getting smaller and smaller. The sides here are only about a half. Okay. The perimeter is getting closer and closer to 2 pi. We're up to 6.2 something. 2 pi is 6.28. Not bad after 12 sides. And the area 3, well, we know pi is 3.141. So at least we got the first digit after 12 sides. And I think I've programmed this thing up to 24 sides. I stopped. Okay, here we are at 24 sides. The height is way out here at 0.991. The little side here is only about a quarter. And the circumference, adding up all these different, I'm sorry, the perimeter of this figure, you can't even see it. It just melds into the circle. The sides are so small. Perimeter is not bad, very close to 2 pi. I think 2 pi is 6.28. So we're at 6.26, not too bad. And pi, of course, which is the area, the sum of all the areas of these triangles that I'm adding up. I've got 24 triangles here, so I take the area and multiply by 24, and the area is 3.106, and we know we're looking for 3.141, et cetera, et cetera. So this idea will work, but how do we make this rigorous? How do we make a pattern that we can follow? This, sure, the computer can do this, and if you have patience, you could do this manually, but we need a pattern to see where this is going, and Antiphon did not have any kind of a pattern to do this. This had to wait for one of the great mathematicians of the ancient world, Euduxus, to make this happen. So let me move on to Euduxus here. Euduxus is a contemporary of Plato. He was actually a student of Plato for a while. He is very famous in the history of mathematics and science. He is considered the greatest mathematician, before Archimedes, and the second with Archimedes. And that's saying a lot, as you can imagine. He's known for three great things that come down to us. One is this method of exhaustion. This is the precursor of integration. Okay, we're going to look at this in detail with Archimedes. We're not going to look at how this was done in Euclid. Euclid takes Euduxus's method and shows how it's done, but I'm going to wait until Archimedes, who is the master of the method of exhaustion, to see how it works in some kind of detail. The second idea is we know that most of the algebra of the Greeks is actually done in terms of proportions. Well, the idea of these irrational numbers like the square root of 2, the diagonal of a square, was a real problem for the Greeks, because the radical 2 they realized was not a rational number. So how do you handle these proportions when you've got lengths which are irrational numbers? Euduxus solved this problem by expanding the idea of proportion to allow even the diagonal of a square to enter into their proportional equations. We have no time to look at that. And the third idea is he was also an astronomer. And Plato laid down one of his precepts that everyone followed. He said, build me a mathematical model of the sky. The phrase that comes down to us is save the appearances. Build a model, a geometric model, which predict where the planets and even the stars are in the sky at any given time. Tell me what the sky will look like tomorrow night at 11 o'clock and any other time in the future or in the past. And the first person who actually tackles this problem is Euduxus in the beginning of the great models, which goes through to Aristotle's model, and of course Ptolemy's great model, and finally to Copernicus's model, before that model is broken into bits by Kepler when he moves away from the circles and starts talking about ellipses. This is where these circular models, where the Earth is in the center, begins with the work of Euduxus. And this, of course, we have no time to talk about. The last problem, the third problem, and the great, so that business of Antiphon gives us the idea of the method of exhaustion. Okay, another new innovation in the idea of mathematics. That method is actually formalized and developed by Euduxus and put into the hands of Archimedes. It becomes basically the integral calculus. The third problem, which leads to another great innovation, and this is the end of our presentation here, will be the doubling of the cube. This is called the Delanian problem, comes from a myth that the Athenians were suffering from a great plague, and they wanted to know what they could do to end the plague, kind of very timely for us, living through 2 years of a plague, a deadly plague. And so they went to the Oracle of Delphi, and they asked the Oracle, what can we do to stop this great surge? And according to legend, the Oracle said, take the altar of Jupiter and double it. Double the volume of that altar. And if you can construct that altar, Jupiter will end the plague for you. And this is where the source of this problem comes from. It's a nice story. Whether that was really the source of why mathematicians began to tackle this, we don't know. But it's one of those stories that if it's not true, it ought to be. And so again, we have the problem of doubling a volume is not easy, because volume is length times width times height. You need to have a number that when you cube it gives you 2. That's a hard number. That's the cube root of 2. That's a tough number. That's an irrational number. And that's what this problem sets out to do. Again, you wouldn't think it was so hard because to double a square is not all that hard, even though, what you need, the double of a square would be an area of 2. You would need radical 2 times radical 2. Radical 2 times radical 2 is 2. I would need to make a square on radical 2. But turns out that's easy, because from the Pythagorean theorem, radical 2 is nothing more than diagonal of the simple square. You get radical 2 for free, right? So from the Pythagorean theorem, that length is radical 2, and it's very easy to construct the square on that length. So from this, it's kind of, well, okay, wouldn't it be kind of as easy to construct, the cube root of 2? Well, it turns out it's not. It turns out that you can't do it with these kinds of mechanisms such as ruler and compass. But our friend Hippocrates, way back, did find an avenue of how this could be done. And he found it in a very pretty way. He said, we're looking for this number x, right? Which has the property that multiplied by itself 3 times gives you the number 2. He claims that if you take number x and y, where 1 over x is to x over y is to y over 2, if you can get that joint proportion, then x will be the cube root of 2. It's a very nice symmetric proportion. If you can find numbers x and y so that 1 is to x, as x is to y, as y is to 2, if you can solve that for x, you will get the cube root of 2. Now, how you do that is another question. And this leads us to the great third-grade innovation that the classical Greek mathematicians did in pursuing the idea of Hippocrates. So let me show you, first of all, why Hippocrates is right, and then I'll show you the great innovation, and then we're basically done with this presentation. It's called the 2 mean proportionals. X and y are the mean proportionals between 1 and 2. So let's take those 2 equations. We have really 2 equations there. 1 over x equals x over y. That's one equation. And then start in the middle. X over y is equal to y over 2. 2 equations. Okay, cross multiply both of them. Cross multiply the first equation and you'll get y is equal to x squared. Cross multiply the second equation and you get y squared is equal to 2x. Now I can write y squared in 2 different ways. I can write y squared on this side as 2x. I can also write y squared as x squared squared, right? So y squared is not only 2x, but y squared is also x to the 4th. Solving this little equation, yes, indeed, x is equal to the cube root of 2. Okay, so Hippocrates is right. X, the cube root of 2, is the first of the 2 mean proportionals of 1 and 2. Okay. Now, of course, he did not solve it exactly this way. I'm using the modern algebra to do this because we can follow it. This is an anachronism, and I have even a worse anachronism here. This idea of finding the 2 mean proportional led to the development of the conic sections. Yeah, this is where the conic sections began, by thinking about cutting the cone in these different areas. The mathematician by the name of Menaechmus, who lived after Plato, in thinking about trying to create these 2 mean proportionals, I don't know how, came up with the idea of cutting the cone in different areas to find this kind of a joint ratio. And talk about a bad anachronism, let's go to our analytic geometry to draw those 2 equations. Y is equal to x squared and 2x is equal to y squared, okay? I make no apologies. I'm not going to cut wooden blocks for us. There's no way we're going to follow that, okay? This is our favorite parabola, of course, y is equal to x squared, and this is just a sideways version. And it turns out that x is, in fact, in the analytic geometry, this is the cube root of 2. And you can verify that the intersection point does agree that the intersection point does give you the x value of the cube root of 2. So yes, we're a long way going from this picture here to this picture here. We know that, but this picture here, to begin the study of conic sections, begins, according to the historians of mathematics, with Menaechmus, thinking about this double ratio of Hippocrates, and somehow or other seeing that in these kinds of cuts. I don't pretend to know how he did it. I don't quite know if the historians of mathematics know how he saw the connection, but there it is. Okay, so what can we say about the legacy of the classical Greeks? Why do I keep saying the classical Greeks? Because we have a whole other layer of Greek mathematics and Greek science to go once we come to the era of Alexander the Great. Alexander the Great is one of the great dividing lines in history, and particularly he is the tremendous dividing line in the history of science. And the science after Alexander the Great, centered on Alexandria, is very different than the kind of math and science centered in Athens before him. So this is just the legacy of the classical Greeks. Next presentation will be entirely focused on the work of Archimedes. So what can we say about what the classical Greeks have left us? They established a study of logic. as an independent science. They established the field of pure mathematics, divided into both geometry and number theory, and we saw a little bit of both of that. They defined the structure of pure mathematics as an axiomatic deductive system. The iconic example of that is Euclid Elements, still followed to this day, that kind of model. And establishing the precedence of geometry over algebra. It lasted until the beginning of our era that we're interested in, the 17th century, the 1600s. Geometry took a precedence over algebra, and that had a great influence on the kind of mathematics that was developed. Geometry was developed far more than algebra was developed, and that has a great consequence for our story of where calculus could finally be born. Right? It finally gets to be born when the algebra catches up to the geometry, when we have analytic geometry. And where does this lead? Well, on the one sense, when we pass the era of Alexander the Great, it leads to an incredible birth of science, of the use of mathematics in science. And these are some of the great milestones of that work between 300 BC and 300 AD, after the classical period. And we have the science of statics and hydrostatics being invented by Archimedes. Optics begins to be studied by Euclid and a man by the name of Heron, who we'll see. The great maps of the world begin to be developed. Cartography and surveying begins to be developed. Ptolemy had a great role to play with that, besides his model of the solar system. Calculations of the size of the Earth and the distance to the sun and the moon are being done. These are wonderful works which I've covered in other courses which I've taught. And finally, the geometric models of the heavens, right? Ending with the work of Ptolemy, the work that Copernicus had to overturn. We're not going to look at this work. We're not going to look at this applied work. We're going to stay with the pure mathematics of the work of the Hellenistic Greeks, as they're called, the Greeks after the time of Alexander. But I just wanted to mention that this is a whole other avenue that this kind of legacy can be built upon. Okay, and those here are the two slides if you're interested in that quadrature proof and Hippocrates' proof. Just a bit more detail, putting in a few more of the steps of the proof if you're interested. Okay, Mike, do we have anything pending here in our chat box?
There were only two messages in chat. The first one was noting that you were breaking up a bit at the beginning.
Yes.
But that cleared up.
Great.
And and the other was just an observation by Dwight that I'll read it. I don't know what amazes me more, the actual math and its formulas, or the questions that had to be posed to allow the math to be developed.
Yeah, isn't it interesting? These three questions, who knows where these, well, we have one myth that comes about the Oracle of Delphi. At least we have one. The other two, who knows where? This is just geometers asking natural questions that they would like to be able to answer. So in that sense, geometers would ask a host of all kinds of questions, but these three particular questions led to such important new developments. The idea of the method of exhaustion, the idea of using motion instead of static locuses, to use motion to define a curve. Archimedes, we'll see, extends this. Archimedes extends everything. And finally, the third one, where the conic sections come from. Because without the conic sections, guys, all we're dealing with here is straight lines and circles. That's all you're going to find in Euclid, is straight lines and circles. You don't get the next level of curve, which is the conic sections, until we get to Menachemimus. And that comes from this, I don't know, this thing of trying to, find the duplication of the cube. So it's incredibly rich how rich these problems were in forcing mathematicians to do this kind of research and push these kinds of boundaries, despite of Plato saying, "Don't go there." Imagine if the mathematicians and scientists, said, "Don't go there." And it took a long time in astronomy. It took a much longer time in astronomy than the mathematicians breaking the rules of Plato. Okay, anybody want to unmute themselves and ask a question before we go on to Archimedes? All right, well, let's get started here. We only have a few minutes. We can get started. I knew I wasn't going to finish it, but I was hoping to get a little bit more, but it is what it is. This is very special to me. He is one of my heroes, my two great heroes in all the work that I've been doing, basically starting this stuff my whole life, the history of math and science. My two great heroes are Archimedes and Galileo. And when we get back to the history of the 17th century, we'll do a little bit of Galileo work. But Archimedes is in fact very, 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 very special because his math is approachable. His math is not this advanced calculus, and you have to have a degree in math to follow it. That's one of the great things about Archimedes, and his work is so profound and so beautiful. So let's get started. The first is, we know that he was also a great engineer, a builder of war machines, and a mathematical physicist. And I hope you get a chance to watch that, at least half of that video about the Drexel professor, who goes through really his work as a mathematical physicist, and then continues on. His premise is that Archimedes was the first scientist to look for a theory of everything, to look for basic underlying principles which can explain many, many things. This is where this idea begins with Archimedes, and he continues on right up through Einstein and beyond. So it's an interesting talk, and the first 30 minutes talks very much about his life, his work in general, and then in particular, his work in hydrostatics, the law of the lever, mechanics, equilibrium, and then hydrostatics with the law of floating bodies. But it's a very interesting talk that I invite you to watch. We're of course focused on his mathematical work, and these are the great works here. The measurement of the circle is probably his most famous. In the real world, in the world of non-mathematicians, this is where he calculates the value of pi to be that 22/7, the approximation that is still used in middle school to this day. That is a number that Archimedes computes. The quadrature of the parabola we already saw. That's those very fancy, very clever triangles being stuck in all over the place using that, set of progression. We'll take a second look at that. We'll look quickly at the volumes of revolution, and then we want to finish with his great work on the sphere and the cylinder. This is the work that he is most proud of, and the work that really blows mathematicians away. This very rich amount of work that we want to spend some time next presentation looking at. And we can't leave without looking at the method, which was discovered. This document was only discovered in 1906. And that talk by the curator of the museum, which actually was given responsibility to take that document and pull it apart and do all that analysis to try to get out all the text. Very, very interesting talk. By the way, the anonymous donor who bought this thing and gave it to the museum to be studied and published for the whole world, everyone thinks that that's Bill Gates, who that anonymous donor is. That's the working theory of the person who bought that for the multi-million dollars. And so we'll talk about the method. And of course, we can't leave Archimedes. We can't leave the beauty of his work without looking at spirals. And again, we will see motion. Since the trajectorics, no one did much with motion, and Archimedes picks up the ball. So this is kind of an outline of what we want to look at. So just a note about his math as a mathematical physicist, because we are going to use the law of the lever. So to remind you of the law of the lever, if we have two weights on a fulcrum, they will balance if the weight times its distance from the fulcrum is equal to the other weight times its distance from the fulcrum. That's why the heavy weight doesn't have to be so far out. So the heavy weight by the smaller distance here from the fulcrum has to balance the lighter weight by the longer distance. And this is the law of the lever. The distance is always taken at the center of gravity. Since these are symmetric bodies, the center of gravity is right in the middle. So it's this point here that we can consider that all of the weight is right there concentrated down. So the center of gravity is an important idea to use in the law of the lever. And here's how you would find different centers of gravity. It's called a centroid. Traditional letter is G for the centroid. And here's one that we will be using. The centroid of a triangle is you draw what's called the medians from the vertex down to the midpoint, from the vertex to the midpoint, and from the vertex to the midpoints. A theorem in Euclid tells us that these three lines cross. They not only cross at a common point, but it is in fact the center of gravity. It is the centrex. That is, you could take this, if this was made out of some kind of thin metal and put a pencil point right there, you could balance it. You could balance it on that point. That is the center of gravity. And we'll actually be using this theorem to find the center of gravity when we get to some of the work of Archimedes. To find a center of gravity of an arbitrary figure, not so easy. Okay? And this is first done by Archimedes using his method of exhaustion. And finally, the law of floating bodies, which we will not need and not get to at all, but to remind you that the weight of buoyancy is equal to the weight of the water displaced by the object when you put it into the liquid. These are two laws that were known in a sense. I don't know if the law of floating bodies was known. Certainly the law of the lever was known for 1,000 years or more before Archimedes, but he's the one who proves it using a set of axioms and theorems. And of course, uses it in a way beyond anyone ever thought of using it to find centers of gravity of simple figures like this. Okay.
Peter, a quick
yes.
question.
Yes.
So the weight of floating bodies, that surely wouldn't be the same between salt water and fresh water, would it?
No, because the weight of the water is different. Absolutely. Since the weight of the water displaced is so much greater, then you can have heavier things floating in salt water. But the force of buoyancy is the weight of the water displaced, whatever that water is. And salt water is heavier, and therefore it'll displace more weight.
I got it. Thank you.
Okay. And in fact, that's why balloons rise, because the balloon will push away the air, and the force of buoyancy under the balloon is equal to the weight of the air displaced. The law is quite general for any fluid where air acts as a fluid. We've seen this before, and I'll just start this. We won't finish it, but we've seen this wonderful construction of Archimedes taking that central triangle, taking the tangent line, which is parallel to the base, and creating this triangle, and then doing doing his magic of stuffing in the triangles using a progression. Here with the one triangle that he finds that these other triangles stuff in at 1/8 the size of them, and the other ones is 1/8 squared of the size, and he gets this progression. We'll look at this again next time and pick it up from here. And of course, we'll get the same result of that wonderful 4/3 of the area of that central triangle ABC. So let's stop here, and certainly we'll have enough time next time to finish the work of Archimedes, and I'll send you out next time the next presentation, which hopefully will start at the end of next Thursday. Okay, any questions or comments at all about anything that we have done so far? I know this has been a lot. I hope that you see the relevance of the work that we did with the ancient Greeks, that we are talking about the mathematics of the calculus in maybe a primitive way, maybe in a specialized way, but it is there. Clearly, the ideas are there, and we'll see this absolutely in the work of Archimedes. I mean, the area stuff is in fact integration, and he does the first work in differentiation, as we'll see in his work on tangents when we look at his beautiful work on spirals. So yes, this is very much a presentation on the beginning of calculus when we work with the stuff of Archimedes. So any questions, any comments before we go? Okay, I don't know.
Just
is
have
it-
one.
Yes,
Sorry, I just have a comment because what I hoped was to get wider parameters for my understanding of the universe. And boy, I was thinking about that phrase about something not being rocket science and how everybody denigrates that. And I never even thought about it, but I'm beginning to understand the volume of calculations to determine to quantify all of the variables necessary to manage to throw something big and heavy off the Earth's gravity. And that is, it's something that I now understand as a truth, not just a funny joke. Thank you.
okay, all right. All right, guys, with that wonderful comment, I'll pause I'll stop the recording unless someone else has anything to say. Are we done? All right, guys, have a good week. Yes, someone? No?
Well, I was going to say amen to Antonia, but she's a woman, so I'll say a woman.
All right.
That is an excellent observation. Throwing something off Earth and getting it out into outer space requires an incredible amount of mathematical calculation.
And just to follow on that, that ain't nothing. Now you have to take that little rock and land it on a comet, which is heading towards Jupiter. Are you kidding me? Oh, yeah. Okay, guys, with that, have a good week.